Unicode.
Unicode is a computing industry standard for the consistent encoding, representation and handling of text expressed in most of the world's writing systems. Developed in conjunction with the Universal Character Set Standard and published in book form as the Unicode Standard, the latest version of Unicode contains a repertoire of more than 110,000 characters covering 100 scripts and various symbols. The standard consists of a set of code charts for visual reference, an encoding method and set of standard character encodings, a set of reference data computer files, and a number of related items, such as character properties, rules for normalization, decomposition, collation, rendering, and bidirectional display order. As of September 2013, the most recent version is Unicode 6.3. The standard is maintained by the Unicode Consortium. Unicode's success at unifying character sets has led to its widespread and predominant use in the internationalization and localization of computer software. The standard has been implemented in many recent technologies, including modern operating systems, XML, the Java programming language, and the Microsoft .NET framework. Unicode can be implemented by different character encodings. The most commonly used encodings are UTF-8, UTF-16 and the now obsolete UCS2. UTF-8 uses 1 byte for any ASCII characters, all of which have the same code values in both UTF-8 and ASCII encoding, and up to 4 bytes for other characters. UCS2 uses a 16-bit code unit, 2 8-bit bytes, for each character but cannot encode every character in the current Unicode standard. UTF-16 extends UCS2, using one 16-bit unit for the characters that were representable in UCS2 and two 16-bit units, for x 8-bit, to handle each of the additional characters.
Origin and development.
Unicode has the explicit aim of transcending the limitations of traditional character encodings, such as those defined by the ISO 8859 standard, which find wide usage in various countries of the world, but remain largely incompatible with each other. Many traditional character encodings share a common problem in that they allow bilingual computer processing, usually using Latin characters in the local script, but not multilingual computer processing of arbitrary scripts mixed with each other. Unicode, in intent, encodes the underlying characters, graphemes and grapheme-like units, rather than the variant glyphs, renderings, for such characters. In the case of Chinese characters, this sometimes leads to controversies over distinguishing the underlying character from its variant glyphs, see Han unification. In text processing, Unicode takes the role of providing a unique code point, a number, not a glyph, for each character. In other words, Unicode represents a character in an abstract way and leaves the visual rendering, size, shape, font, or style, to other software, such as a web browser or word processor. This simple aim becomes complicated, however, because of concessions made by Unicode's designers in the hope of encouraging a more rapid adoption of Unicode. The first 256 code points were made identical to the content of ISO 8859-1 so as to make it trivial to convert existing Western text. Many essentially identical characters were encoded multiple times at different code points to preserve distinctions used by legacy encodings and therefore, allow conversion from those encodings to Unicode, and back, without losing any information. For example, the full-width forms section of code points encompasses a full Latin alphabet that is separate from the main Latin alphabet section. In Chinese, Japanese, and Korean, CJK, fonts, these characters are rendered at the same width as CJK ideographs, rather than at half the width. For other examples, see duplicate characters in Unicode.
History.
The origins of Unicode date to 1987, when Joe Becker from Xerox and Lee Collins and Mark Davis from Apple started investigating the practicalities of creating a universal character set. In August 1988, Joe Becker published a draft proposal for an international multilingual text character encoding system, tentatively called Unicode. Although the term Unicode had previously been used for other purposes, such as the name of a programming language developed for the UNIVC in the late 1950s, and most notably a universal telegraphic phrase book that was first published in 1889. Becker may not have been aware of these earlier usages, and he explained that the name Unicode is intended to suggest a unique, unified, universal encoding. In this document, entitled Unicode 88, Becker outlined a 16-bit character model. His original 16-bit design was based on the assumption that only those scripts and characters in modern use would need to be encoded. In early 1989, the Unicode Working Group expanded to include Ken Whistler and Mike Knagan of Metaphor, Karen Smith Yoshimura and Joan Alapprand of RLG, and Glenn Wright of Sun Microsystems, and in 1990 Michelle Sunad and Asmus Freitag from Microsoft and Rick McGowan of Next joined the group. By the end of 1990, most of the work on mapping existing character encoding standards had been completed, and a final review draft of Unicode was ready. The Unicode Consortium was incorporated on January 3, 1991, in California, and in October 1991, the first volume of the Unicode Standard was published. The second volume, covering Han ideographs, was published in June 1992. In 1996, a surrogate character mechanism was implemented in Unicode 2.0, so that Unicode was no longer restricted to 16 bits. This increased the Unicode codespace to over 1 million code points, which allowed for the encoding of many historic scripts, for example Egyptian hieroglyphs, and thousands of rarely used or obsolete characters that had not been anticipated as needing encoding. Among the characters not originally intended for Unicode are rarely used kanji or Chinese characters, many of which are part of personal and place names, making them rarely used, but much more essential than envisioned in the original architecture of Unicode.
Architecture and terminology.
Unicode defines a codespace of 1,114,112 code points in the range 0 hex to 10 FFFFHEX. Normally a Unicode code point is referred to by writing U+ followed by its hexadecimal number. For code points in the basic multilingual plane, BMP, 4 digits are used, for example U+0058 for the character Latin capital letter X. For code points outside the BMP, 5 or 6 digits are used, as required, for example U+E0001 for the character language TAG and U+10FFFD for the character private use character 10FFFD. Older versions of the standard used similar notations but with slightly different rules. For example, Unicode 3.0 used U followed by 8 digits to indicate a code point, and allowed U+ to be used only with exactly 4 digits to indicate a code unit, such as a single byte of a multi-byte UTF-8 encoding of a code point.
Code point planes and blocks.
The Unicode codespace is divided into 17 planes, numbered 0 to 16. All code points in the BMP are accessed as a single code unit in UTF-16 encoding and can be encoded in 1, 2 or 3 bytes in UTF-8. Code points in planes 1 through 16, supplementary planes, or, informally, astral planes, are accessed as surrogate pairs in UTF-16 and encoded in 4 bytes in UTF-8. Within each plane, characters are allocated within named blocks of related characters. Although blocks are an arbitrary size, they are always a multiple of 16 code points and often a multiple of 128 code points. Characters required for a given script may be spread out over several different blocks.
Character general category.
Each code point has a single general category property. The major categories are letter, mark, number, punctuation, symbol, separator and other. Within these categories, there are subdivisions. The general category is not useful for every use, since legacy encodings have used multiple characteristics per single code point. For example U+000A less than control 000 a greater than line feed, LF, in ASCII is both a control and a formatting separator. In Unicode the general category is other, control. Often, other properties must be used to specify the characteristics and behavior of a code point. The possible general categories are: code points in the range U plus D800 U plus DBFF, 1024 code points, are known as high surrogate code points, and code points in the range U plus DC00 U plus DFFF, 1024 code points, are known as low surrogate code points. A high surrogate code point, also known as a leading surrogate, followed by a low surrogate code point, also known as a trailing surrogate, together form a surrogate pair used in UTF-16 to represent 1,048,576 code points outside BMP. High and low surrogate code points are not valid by themselves. Thus the range of code points that are available for use as characters is U plus 0000 U plus D7FF and U plus E000 U plus 10FFFF, 1,112,064 code points. The value of these code points, that is excluding surrogates, is sometimes referred to as the character's scalar value. Certain non-character code points are guaranteed never to be used for encoding characters, although applications may make use of these code points internally if they wish. There are 66 non-characters, U plus FDDO, U plus FDEF, and any code point ending in the value FFFE or FFFF, that is U plus FFFE, U plus FFFF, U plus 1 FFFE, U plus 1 FFFF, U plus 10 FFFE, U plus 10 FFFF. The set of non-characters is stable, and no new non-characters will ever be defined. Reserved code points are those code points which are available for use as encoded characters, but are not yet defined as characters by Unicode. Private use code points are considered to be assigned characters, but they have no interpretation specified by the Unicode Standard, so any interchange of such characters requires an agreement between sender and receiver on their interpretation. There are three private use areas in the Unicode code space. Private use area, U plus E000 U plus F8FF, 6,400 characters. Supplementary private use area A, U plus F000 U plus FFFFD, 65,534 characters. Supplementary private use area B, U plus 100,000 U plus 10 FFFD, 65,534 characters. Graphic characters are characters defined by Unicode to have a particular semantic, and either have a visible glyph shape or represent a visible space. As of Unicode 6.3 there are 109,975 graphic characters. Format characters are characters that do not have a visible appearance, but may have an effect on the appearance or behavior of neighboring characters. For example, U plus 200C0 width non-joiner and U plus 200D0 width joiner may be used to change the default shaping behavior of adjacent characters, for example to inhibit ligatures or request ligature formation. There are 147 format characters in Unicode 6.3. 65 code points, U plus 0000 U plus 001F and U plus 007F U plus 009F, are reserved as control codes, and correspond to the CO and C1 control codes defined in ISO IEC 6429. Of these U plus 0009, tab, U plus 000A, line feed, and U plus 000D, carriage return, are widely used in Unicode encoded texts. Graphic characters, format characters, control code characters, and private use characters are known collectively as assigned characters.
Abstract characters.
The set of graphic and format characters defined by Unicode does not correspond directly to the repertoire of abstract characters that is representable under Unicode. Unicode encodes characters by associating an abstract character with a particular code point. However, not all abstract characters are encoded as a single Unicode character, and some abstract characters may be represented in Unicode by a sequence of two or more characters. For example, a Latin small letter I with an agonek, a dot above, and an acute accent, which is required in Lithuanian, is represented by the character sequence U plus 012F, U plus 0307, U plus 0301. Unicode maintains a list of uniquely named character sequences for abstract characters that are not directly encoded in Unicode. All graphic, format, and private use characters have a unique and immutable name by which they may be identified. This immutability has been guaranteed since Unicode version 2.0 by the name stability policy. In cases where the name is seriously defective and misleading, or has a serious typographical error, a formal alias may be defined, and applications are encouraged to use the formal alias in place of the official character name. For example, U+A015 Wu Yi syllable Wu has the formal alias Yi syllable iteration mark, and U+F18. Presentation form for vertical right white lenticular bracket, SIC, has the formal alias presentation form for vertical right white lenticular bracket.
Unicode Consortium.
The Unicode Consortium is a non-profit organization that coordinates Unicode's development. Full members include most of the main computer software and hardware companies with any interest in text processing standards, including Adobe Systems, Apple, Google, IBM, Microsoft, Oracle Corporation, Yahoo! And the Ministry of Endowments and Religious Affairs of Sultanate of Oman. The consortium has the ambitious goal of eventually replacing existing character encoding schemes with Unicode and its standard Unicode Transformation Format, UTF, schemes, as many of the existing schemes are limited in size and scope and are incompatible with multilingual environments.
Versions.
Unicode is developed in conjunction with the International Organization for Standardization and shares the character repertoire with ISO IEC 10646, the Universal Character Set. Unicode and ISO IEC 10646 function equivalently as character encodings, but the Unicode standard contains much more information for implementers, covering, in depth, topics such as bitewise encoding, collation and rendering. The Unicode standard enumerates a multitude of character properties, including those needed for supporting bidirectional text. The two standards do use slightly different terminology. The consortium first published the Unicode Standard, ISBN 0-321-18578-1, in 1991 and continues to develop standards based on that original work. The latest version of the standard, Unicode 6.3, was released in September 2013 and is available from the consortium's website. The last of the major versions, versions X0, to be published in book form was Unicode 5.0, ISBN 0-321-48091-0, but since Unicode 6.0 the full text of the standard is no longer being published in book form. In 2012, however, it was announced that only the core specification for Unicode version 6.1 would be made available as a 692-page print-on-demand paperback. Unlike the previous major version printings of the standard, the print-on-demand core specification does not include any code charts or standard annexes, but the entire standard, including the core specification, will still remain freely available on the Unicode website. Thus far the following major and minor versions of the Unicode standard have been published. Update versions, which do not include any changes to character repertoire, are signified by the third number, for example version 4.0.1, and are omitted in the table below. The next version of the Unicode standard is currently planned as version 7.0, expected to be released in July 2014.
Scripts covered.
Unicode covers almost all scripts, writing systems, in current use today. Although 100 scripts are included in the latest version of Unicode, covering alphabets, abugidas and syllabaries, many more are yet to be encoded, particularly those mainly used in historical, liturgical, and academic contexts. Further additions of characters to the already encoded scripts, as well as symbols, in particular for mathematics and music, in the form of notes and rhythmic symbols, also occur. The Unicode Roadmap Committee, Michael Everson, Rick McGowan, and Ken Whistler, maintain the list of scripts that are candidates or potential candidates for encoding and their tentative code block assignments on the Unicode Roadmap page of the Unicode Consortium website. For some scripts on the roadmap, such as Jurchen, Nushu, Tangut, and Linear, encoding proposals have been made and they are working their way through the approval process. For other scripts, such as Mayan and Rongo Rongo, no proposal has yet been made, and they await agreement on character repertoire and other details from the user communities involved. Some modern invented scripts which have not yet been included in Unicode, for example, Tengwa, or which do not qualify for inclusion in Unicode due to lack of real-world use, for example, Klingon, are listed in the conscript Unicode registry, along with unofficial but widely used private use area code assignments. There is also a medieval Unicode font initiative focused on special Latin medieval characters. Part of these proposals have been already included into Unicode. The Script Encoding Initiative, a project run by Dr. Deborah Anderson at the University of California, Berkeley, was founded in 2002 with the goal of funding proposals for scripts not yet encoded in the standard. The project has become a major source of proposed additions to the standard in recent years.
Mapping and encodings.
Several mechanisms have been specified for implementing Unicode. The choice depends on available storage space, source code compatibility, and interoperability with other systems.
Unicode transformation format and universal character set.
Unicode defines two mapping methods, the Unicode transformation format, UTF, encodings, and the universal character set, UCS, encodings. An encoding maps, possibly a subset of, the range of Unicode code points to sequences of values in some fixed size range, termed code values. The numbers in the names of the encodings indicate the number of bits in one code value, for UTF encodings, or the number of bytes per code value, for UCS, encodings. UTF-8 and UTF-16 are probably the most commonly used encodings. UCS-2 is an obsolete subset of UTF-16. UCS-4 and UTF-32 are functionally equivalent. UTF encodings include UTF-1, a retired predecessor of UTF-8, maximizes compatibility with ISO 2022, no longer part of the Unicode Standard. UTF-7, a 7-bit encoding sometimes used in email, often considered obsolete, not part of the Unicode Standard, but only documented as an informational RFC, that is not on the Internet Standards track either. UTF-8, an 8-bit variable width encoding which maximizes compatibility with ASCII. UTF-IBGDIC, an 8-bit variable width encoding similar to UTF-8, but designed for compatibility with IBGDIC. Not part of the Unicode Standard. UTF-16, a 16-bit, variable width encoding. UTF-32, a 32-bit, fixed width encoding. UTF-8 uses 1 to 4 bytes per code point and, being compact for Latin scripts and ASCII compatible, provides the de facto standard encoding for interchange of Unicode text. It is also used by FreeBSD and most recent Linux distributions as a direct replacement for legacy encodings and general text handling. The UCS2 and UTF-16 encodings specify the Unicode byte order mark, BOM, for use at the beginnings of text files, which may be used for byte ordering detection, or byte endianness detection. The BOM, code point U plus FEFF, has the important property of unambiguity on byte reorder, regardless of the Unicode encoding used. U plus FFFE, the result of byte swapping U plus FEFF, does not equate to a legal character, and U plus FEFF in other places, other than the beginning of text, conveys the zero-width non-break space, a character with no appearance and no effect other than preventing the formation of ligatures. The same character converted to UTF-8 becomes the byte sequence EFBBBF. The Unicode Standard allows that the BOM can serve as signature for UTF-8 encoded text where the character set is unmarked. Some software developers have adopted it for other encodings, including UTF-8, in an attempt to distinguish UTF-8 from local 8-bit code pages. However, RFC 3629, the UTF-8 standard, recommends that byte order marks be forbidden in protocols using UTF-8, but discusses the cases where this may not possible. In addition, the large restriction on possible patterns in UTF-8, For instance, there cannot be any lone bytes with the high bit set, means that it should be possible to distinguish UTF-8 from other character encodings without relying on the BOM. In UTF-32 and UCS4, one 32-bit code value serves as a fairly direct representation of any character's code point, although the NDRness, which varies across different platforms, affects how the code value manifests as an octet sequence. In the other encodings, each code point may be represented by a variable number of code values. UTF-32 is widely used as an internal representation of text in programs, as opposed to stored or transmitted text, since every Unix operating system that uses the GCC compilers to generate software uses it as the standard wide character encoding. Some programming languages, such as Seed7, use UTF-32 as internal representation for strings and characters. Recent versions of the Python programming language, beginning with 2.2, may also be configured to use UTF-32 as the representation for Unicode strings, effectively disseminating such encoding in high-level coded software. Unicode, another encoding form, enables the encoding of Unicode strings into the limited character set supported by the ASCII-based domain name system. The encoding is used as part of IDNA, which is a system enabling the use of internationalized domain names in all scripts that are supported by Unicode. Earlier and now historical proposals include UTF-5 and UTF-6. GB18030 is another encoding form for Unicode, from the Standardization Administration of China. It is the official character set of the People's Republic of China, PRC. BOCU1 and SCSU are Unicode compression schemes. The April Fool's Day RFC of 2005 specified two parody UTF encodings, UTF-9 and UTF-18.
Ready-made versus composite characters.
Unicode includes a mechanism for modifying character shape that greatly extends the supported glyph repertoire. This covers the use of combining diacritical marks. They are inserted after the main character. Multiple combining diacritics may be stacked over the same character. Unicode also contains pre-composed versions of most letter diacritic combinations in normal use. These make conversion to and from legacy encodings simpler, and allow applications to use Unicode as an internal text format without having to implement combining characters. For example, E can be represented in Unicode as U+0065, Latin small letter e, followed by U+0301, combining acute accent, but it can also be represented as the pre-composed character U+00E9, Latin small letter e with acute. Thus, in many cases, users have multiple ways of encoding the same character. To deal with this, Unicode provides the mechanism of canonical equivalence. An example of this arises with Hangul, the Korean alphabet. Unicode provides a mechanism for composing Hangul syllables with their individual subcomponents, known as Hangul JMO. However, it also provides 11,172 combinations of pre-composed syllables made from the most common JMO. The CJK ideographs currently have codes only for their pre-composed form. Still, most of those ideographs comprise simpler elements, often called radicals in English, so in principle, Unicode could have decomposed them, as it did with Hangul. This would have greatly reduced the number of required code points, while allowing the display of virtually every conceivable ideograph, which might do away with some of the problems caused by the Han unification. A similar idea covers some input methods, such as kanji and wabai. However, attempts to do this for character encoding have stumbled over the fact that ideographs do not decompose as simply or as regularly as it seems they should. A set of radicals was provided in Unicode 3.0, CJK radicals between U+2E80 and U+2EFF, Kangxi radicals in U+2F00 to U+2FDF, and ideographic description characters from U+2FF0 to U+2FFB, but the Unicode Standard, CH 12.2 of Unicode 5.2 warns against using ideographic description sequences as an alternate representation for previously encoded characters.
Ligatures.
Many scripts, including Arabic and Devanagari, have special orthographic rules that require certain combinations of letter forms to be combined into special ligature forms. The rules governing ligature formation can be quite complex, requiring special script shaping technologies such as ACE, Arabic Calligraphic Engine by Decotype in the 1980s, and used to generate all the Arabic examples in the printed editions of the Unicode Standard, which became the proof of concept for OpenType, by Adobe and Microsoft, Graphite, by SIL International, or AAT, by Apple. Instructions are also embedded in fonts to tell the operating system how to properly output different character sequences. A simple solution to the placement of combining marks or diacritics is assigning the marks a width of 0 and placing the glyph itself to the left or right of the left side of bearing, depending on the direction of the script they are intended to be used with. A mark handled this way will appear over whatever character precedes it, but will not adjust its position relative to the width or height of the base glyph. It may be visually awkward and it may overlap some glyphs. Real stacking is impossible, but can be approximated in limited cases. For example, tie top combining vowels and tone marks can just be at different heights to start with. Generally this approach is only effective in monospaced fonts, but may be used as a fallback rendering method when more complex methods fail.
Standardized subsets.
Several subsets of Unicode are standardized. Microsoft Windows. Since Windows NT 4.0 supports WGL4 with 652 characters, which is considered to support all contemporary European languages using the Latin, Greek, or Cyrillic script. Other standardized subsets of Unicode include the multilingual European subsets, MES1, Latin scripts only, 335 characters, MES2, Latin, Greek and Cyrillic 1062 characters, and MES3A and MES3B, two larger subsets, not shown here. Note that MES2 includes every character in MES1 and WGL4. Rendering software which cannot process a Unicode character appropriately often displays it as an open rectangle, or the Unicode replacement character, U+FFFD, to indicate the position of the unrecognized character. Some systems have made attempts to provide more information about such characters. The Apple Last Resort font will display a substitute glyph indicating the Unicode range of the character, and the SIL Unicode fallback font will display a box showing the hexadecimal scalar value of the character.
Unicode in use. Operating systems.
Unicode has become the dominant scheme for internal processing and storage of text. Although a great deal of text is still stored in legacy encodings, Unicode is used almost exclusively for building new information processing systems. Early adopters tended to use UCS2 and later moved to UTF-16, as this was the least disruptive way to add support for non-BMP characters. The best-known such system is Windows NT, and its descendants, Windows 2000, Windows XP, Windows Vista and Windows 7, which uses UTF-16 as the sole internal character encoding. The Java and .NET bytecode environments, Mac OS X, and KDE also use it for internal representation. Unicode is available on Windows 95, and its descendants, Windows 98 and Windows ME, through Microsoft Lair for Unicode. UTF-8, originally developed for Plan 9, has become the main storage encoding on most Unix-like operating systems, though others are also used by some libraries, because it is a relatively easy replacement for traditional extended ASCII character sets. UTF-8 is also the most common Unicode encoding used in HTML documents on the World Wide Web. Multilingual text rendering engines which use Unicode include Uniscribe and DirectWrite for Microsoft Windows, ATSUI and Cortext for Mac OS X, and Pango for GTK Plus and the GNOME desktop.
Input methods.
Because keyboard layouts cannot have simple key combinations for all characters, several operating systems provide alternative input methods that allow access to the entire repertoire. ISO 14755, which standardizes methods for entering Unicode characters from their code points, specifies several methods. There is the basic method, where a beginning sequence is followed by the hexadecimal representation of the code point and the ending sequence. There is also a screen selection entry method specified, where the characters are listed in a table in a screen, such as with a character map program.
Email.
MIME defines two different mechanisms for encoding non-ASCII characters in email, depending on whether the characters are in email headers, such as the subject, or in the text body of the message. In both cases, the original character set is identified as well as a transfer encoding. For email transmission of Unicode, the UTF-8 character set and the base 64 or the quoted printable transfer encoding are recommended, depending on whether much of the message consists of ASCII characters. The details of the two different mechanisms are specified in the MIME standards and generally are hidden from users of email software. The adoption of Unicode in email has been very slow. Some East Asian text is still encoded in encodings such as ISO 2022, and some devices, such as mobile phones, still cannot handle Unicode data correctly. Support has been improving, however. Many major free mail providers such as Yahoo, Google, Gmail, and Microsoft, Hotmail, support it.
Web.
All W3C recommendations have used Unicode as their document character set since HTML 4.0. Web browsers have supported Unicode, especially UTF-8, for many years. Display problems result primarily from font-related issues. In particular, versions of Microsoft Internet Explorer do not render many code points unless explicitly told to use a font that contains them. Although syntax rules may affect the order in which characters are allowed to appear, XML, including XHTML, documents, by definition, comprise characters from most of the Unicode code points, with the exception of most of the CO control codes, the permanently unassigned code points D800 DFFF, FFFE or FFFF. HTML characters manifest either directly as bytes according to documents encoding, if the encoding supports them, or users may write them as numeric character references based on the character's Unicode code point. For example, the references in number 916, and number 1049, and number 1511, and number 1605, and number 3671, and number 12354, and number 21494, and number 33865, and a number 47568. Or the same numeric values expressed in hexadecimal, with index as the prefix, should display on all browsers as D, I, Q, M, 7, A, Xi, Xi, and Mal. When specifying URIs, for example as URLs in HTTP requests, non-ASCII characters must be %encoded.
Fonts.
Free and retail fonts based on Unicode are widely available, since TrueType and OpenType support Unicode. These font formats map Unicode code points to glyphs. Thousands of fonts exist on the market, but fewer than a dozen fonts, sometimes described as pan-Unicode fonts, attempt to support the majority of Unicode's character repertoire. Instead, Unicode-based fonts typically focus on supporting only basic ASCII and particular scripts or sets of characters or symbols. Several reasons justify this approach. Applications and documents rarely need to render characters from more than one or two writing systems. Fonts tend to demand resources in computing environments. And operating systems and applications show increasing intelligence in regard to obtaining glyph information from separate font files as needed, that is font substitution. Furthermore, designing a consistent set of rendering instructions for tens of thousands of glyphs constitutes a monumental task. Such a venture passes the point of diminishing returns for most typefaces.
New lines.
Unicode partially addresses the new line problem that occurs when trying to read a text file on different platforms. Unicode defines a large number of characters that conforming applications should recognize as line terminators. In terms of the new line, Unicode introduced U+2028 line separator and U+2029 paragraph separator. This was an attempt to provide a Unicode solution to encoding paragraphs and lines semantically, potentially replacing all of the various platform solutions. In doing so, Unicode does provide a way around the historical platform-dependent solutions. Nonetheless, few if any Unicode solutions have adopted these Unicode line and paragraph separators as the sole canonical line-ending characters. However, a common approach to solving this issue is through new line normalization. This is achieved with the Cocoa text system in Mac OS X and also with W3C XML and HTML recommendations. In this approach, every possible new line character is converted internally to a common new line, which one does not really matter since it is an internal operation just for rendering. In other words, the text system can correctly treat the character as a new line, regardless of the input's actual encoding.
Issues. Philosophical incompleteness criticisms.
Han unification, the identification of forms in the East Asian languages which one can treat as stylistic variations of the same historical character, has become one of the most controversial aspects of Unicode, despite the presence of a majority of experts from all three regions and the Ideographic Rapporteur Group, IRG, which advises the Consortium and ISO on additions to the repertoire and on Han unification. Unicode has been criticized for failing to separately encode older and alternative forms of kanji which, critics argue, complicates the processing of ancient Japanese and uncommon Japanese names. This is often due to the fact that Unicode encodes characters rather than glyphs, the visual representations of the basic character that often vary from one language to another. Unification of glyphs leads to the perception that the languages themselves, not just the basic character representation, are being merged. There have been several attempts to create alternative encodings that preserve the stylistic differences between Chinese, Japanese, and Korean characters in opposition to Unicode's policy of Han unification. An example of one is Tron. Although it is not widely adopted in Japan, there are some users who need to handle historical Japanese text and favor it. Although the repertoire of fewer than 21,000 Han characters in the earliest version of Unicode was largely limited to characters in common modern usage, Unicode now includes more than 70,000 Han characters, and work is continuing to add thousands more historic and dialectal characters used in China, Japan, Korea, Taiwan, and Vietnam. Modern font technology provides a means to address the practical issue of needing to depict a unified Han character in terms of a collection of alternative glyph representations, in the form of Unicode variation sequences. For example, the advanced typographic tables of OpenType permit one of a number of alternative glyph representations to be selected when performing the character-to-glyph mapping process. In this case, information can be provided within plain text to designate which alternate character form to select. If the difference in the appropriate glyphs for two characters in the same script differ only in the italic, Unicode has generally unified them, as can be seen in the comparison between Russian, labeled standard, and Serbian characters at right, meaning that the difference had shown through smart font technology or manually changing fonts.
Mapping to legacy character sets.
Unicode was designed to provide code point-by-code point round-trip format conversion to and from any pre-existing character encodings, so that text files in older character sets can be naively converted to Unicode, and then back and get back the same file. That has meant that inconsistent legacy architectures, such as combining diacritics and pre-composed characters, both exist in Unicode, giving more than one method of representing some text. This is most pronounced in the three different encoding forms for Korean Hangul. Since version 3.0, any pre-composed characters that can be represented by a combining sequence of already existing characters can no longer be added to the standard in order to preserve interoperability between software using different versions of Unicode. Injective mappings must be provided between characters in existing legacy character sets and characters in Unicode to facilitate conversion to Unicode and allow interoperability with legacy software. lack of consistency in various mappings between earlier Japanese encodings such as Shift-JIS or EUCJP and Unicode led to round-trip format conversion mismatches, particularly the mapping of the character JIS-X0208 1-33, wave dash, heavily used in legacy database data, to either U+FF5E full width tilde, in Microsoft Windows, or U+301C wave dash, other vendors. Some Japanese computer programmers objected to Unicode because it requires them to separate the use of U+005C \reverse /, and U+00A5Y equals yen sign, which was mapped to 0x5C in JIS-X0201, and a lot of legacy code exists with this usage. This encoding also replaces ~0x7E with overline dash, now 0xAF. The separation of these characters exists in ISO 8859-1, from long before Unicode.
Index scripts.
Index scripts such as Tamil and Devanagari are each allocated only 128 code points, matching the ISCII standard. The correct rendering of Unicode index text requires transforming the stored logical order characters into visual order and the forming of ligatures out of components. Some local scholars argued in favor of assignments of Unicode code points to these ligatures, going against the practice for other writing systems, though Unicode contains some Arabic and other ligatures for backward compatibility purposes only. Encoding of any new ligatures in Unicode will not happen, in part because the set of ligatures is font-dependent, and Unicode is an encoding independent of font variations. The same kind of issue arose for Tibetan script. The Chinese National Standard Organization failed to achieve a similar change. Thai alphabet support has been criticized for its ordering of Thai characters. The vowels e, o, I that are written to the left of the preceding consonant are in visual order instead of phonetic order, unlike the Unicode representations of other index scripts. This complication is due to Unicode inheriting the Thai Industrial Standard 620, which worked in the same way, and was the way in which Thai had always been written on keyboards. This ordering problem complicates the Unicode collation process slightly, requiring table lookups to reorder Thai characters for collation. Even if Unicode had adopted encoding according to spoken order, it would still be problematic to collate words in dictionary order. For example, the word aesdng perform starts with a consonant cluster SD, with an inherent vowel for the consonant S. The vowel E, in spoken order would come after the D, but in a dictionary, the word is collated as it is written, with the vowel following the S.
Combining characters.
Characters with diacritical marks can generally be represented either as a single precomposed character or as a decomposed sequence of a base letter plus one or more non-spacing marks. For example, E, precomposed E with macron and acute above, and E followed by the combining macron above and combining acute above, should be rendered identically, both appearing as an E with a macron and acute accent, but in practice, their appearance may vary depending upon what rendering engine and fonts are being used to display the characters. Similarly, underdots, as needed in the romanization of indic, will often be placed incorrectly. Unicode characters that map to precomposed glyphs can be used in many cases, thus avoiding the problem, but where no precomposed character has been encoded, the problem can often be solved by using a specialist Unicode font such as Caris SIL that uses graphite, OpenType, or AAT technologies for advanced rendering features.